today I'm going to be talking about how we use quantum dots to achieve this photon flying qubit and spin static qubit system. So a quantum dot then is a very small volume of semiconductor. Here I'm showing you an SE image of one of our quantum dots, and these are indium arsenide quantum dots inside gallium arsenide matrix. So the size of these quantum dots is comparable to the Bohr radius of the electron wave function. So what happens here is if you look at the band structure potential, here we have a quantum box here, and you see that the energy levels in the conduction bands and in the valence band become quantized. So this means that the transitions between these levels in the semiconductor undergoes very specific transition energies and involves specific quanta. So in fact, if we absorb a single photon in the system, what happens is we shine a single photon on and we promote electron from the valence band to the conduction band to form what's known as an exciton or an electron hole pair, which has a very specific energy. So this exciton then remains in the quantum dot until it recombines, and this occurs in normal quantum dots over the range of about 1 nanosecond. So a nanosecond lifetime for these quantum dots, excitons, isn't a very long time to store information. In fact, we can probably manipulate these things on a picosecond time scale, but still that doesn't give us enough time to do many operations. So we want to find a better way to store information in these systems. And in fact, we use a single electron spin. Now physically, what we do here is incorporate the spin by putting the electron into the quantum dot permanently. And practically we do that by doping the quantum dots with a layer of dopant material 20 nanometers below the quantum dots, and then we expect that a single electron occupies each of these quantum dots. Now, the electron obviously has a spin, and when it's inside the quantum dot, it'll be orientated either up or down. Now, so here I'm showing the conduction band and the valence band. So here, this is the hole level, and this is the electron level here. Now, quantum dots, because their quantized levels undergo Pauli blocking and have very specific selection rules, and that's very important because that allows us to manipulate them with light. So if you look at the selection rules then, what we find out is if we excite the transition here with a sigma plus polarized photon, so that's circularly polarized, the exciton it wants to absorb, I'm just showing you here, is a down polarized electron and an up polarized hole. So if we have an electron spin which is polarized up, we can see that this transition is allowed because we're pairing the electron spins. However, if the electron spin is polarized down, we see that we want to promote another electron hole pair with the 2 electron spins down, and this state is not allowed. And the effect of this is that this electron spin down transition is effectively transparent to the light. And we can make use of that in order to excite with the light and then either initialize the electron spin, read it out, or even use that as a phase gate. So why use electron spins then? Well, it turns out, and I'll show you in the next few slides, that the coherence time of the electron is much longer than for trion or exciton lifetime. So I forgot to mention a trion is this 3-particle state with 2 electrons in one hole. In fact, I'll show you that they will last for microseconds. So we're able to actually write the electron spin, store it for a microsecond, and then read out that spin later. And quantum dots also have the advantage in that they're a solid-state system. So they're easy to incorporate into solid structures. They're a microscale or even nanoscale devices, and this means that they should be easily scalable without making the system too large. Okay, so next few slides I want to talk about how we can actually measure the electron spin coherence time. So the coherence time is a very important quantity in quantum information systems, because without keeping the coherence, the phase coherence in the system, we can't manipulate the system reliably. So we've got to find a way of measuring the spin coherence of the system. So what we do here is take a quantum dot and excite it with circularly polarized light. And here's a model of the quantum dot. So you have it's a kind of flat structure. You can think of it as a flat cylinder. And we excite an electron which is polarized along what we call the Z direction here. What we then do is apply a magnetic field perpendicular to that direction, in this direction here, and that means that this spin-up polarized electron here is no longer an eigenstate of the system, which means that the electron eigenstates are now parallel or anti-parallel to the field. So if you put the electron spin in this state here, what we see is that this electron will start to precess about this magnetic field. And it will precess at the precession frequency, the Lamour precession frequency, given by the magnetic field strength and the G factor of the electron. Now, what we do here is monitor the population of spin-up and spin-down electrons, and we should see an oscillation in time in this population of the electron spin. And we can actually use that to measure the coherence time, because it will only carry on precessing if this electron spin maintains its coherence. If we see the loss of coherence, we'll see a decay of the oscillation amplitude. Okay, and we actually do that by using a technique called Faraday Rotation. And here, in the first measurements we did, we used an ensemble of quantum dots, which means we use many millions of quantum dots on a bulk piece of semiconductor. So what we do here is excite our sample with a picosecond pulse of circularly polarized light, and that polarizes the quantum dots, the electron spins in our quantum dots in our system. And then we come in with a probe pulse, and this probe pulse is delayed at a controlled time at which we can vary. And by continuously varying this pulse, we get a measure of the spin precession as a function of time. So this probe pulse is linearly polarized, and we actually make use of a kind of Faraday effect in this system, where if you imagine the probe pulse, which is linearly polarized, is a superposition of sigma plus and sigma minus circularly polarized light. And of course, one polarization interacts in a different way to the other. So we get a delay of the sigma plus polarized light with respect to sigma minus. And that effectively gives you, when this probe pulse emerges, a rotation in the linear polarization. And in fact, it's this rotation that we actually measure. So the angle is proportional directly to the electron spin polarization in our sample. And here I'm showing you some Faraday rotation pump probe measurements that we've taken. And I'm showing you several here taken as we're increasing the magnetic field going downwards. Now you can see here that at time t equals 0 we have our pump pulse which initializes the electron spin system. Now there's some complicated behavior close to this pump pulse which I'm not going to explain. But then it wants you to look at behavior after this. So here we're scanning the probe beam and seeing the oscillations in the electron spin from up to down. And it behaves as we expect. We see that the oscillations get faster as we increase the magnetic field as we expect.
Why do you get oscillations before?
I'm going to explain that in a minute, yeah. Okay, so we see that the oscillations decay, and they decay faster for increasing magnetic field. And the reason for that is that the phase between all these electron spins in the ensemble, so we're measuring many quantum dots, each of the precession frequencies is slightly different, so the global phase will begin to be lost. Now, it's important to realize that this is just the global phase between all of the spins in the system, but each single spin in the system may be keeping its own coherence time for much, much longer, but we can't detect it. But there is actually a way of detecting this system, and like you said, we discovered this by looking at the strange behavior that we see here at negative time delay. So we're exciting the pulses here, and these come every 12 nanoseconds. So in fact, the signal that we see here is coming from the last pulse that was 12 nanoseconds ago. Now, this might not be surprising, because if we have a long coherence time, we should still see signal from the last pulse. But we know here, for example, in these high field curves, that the signal seems to decay. So what's going on? It seems to be decaying and then suddenly coming back again, as if it knows the next pulse is coming. Now, the reason this actually occurs is because we do have much longer coherence times than we can measure. And in fact, because we have such long coherence times, the regular pulsing of, okay, it's 13 nanoseconds, I said 12, but okay, it's every 30 nanoseconds this pulse comes, and this regulates the electron spin precession, and it picks out the electron spins which have, what happens is actually it excites only the quantum dots where the electron spins are polarized up, and it doesn't excite the ones where the electron spins are polarized down. So you actually select the quantum dots with exactly the right G factors. So that the precession period is a multiple of the repetition period of the laser. So it's almost like a kind of mode locking effect of the electron spins. And so you can support many of these modes, even though there's a small G factor variation. I'm showing you like an example here where you have slightly different precession frequencies. So you can see now why we see the signal that we do. So at both at the beginning and at the end of these pulses, we see that the signal is in phase, but in the center it's completely dephased. So the global signal oscillations will decrease to the middle and then increase again. And in fact, it should be symmetric. However, eventually this electron spin does decay. And the reason it decays, and particularly at low temperature, is mainly due to the hyperfine interaction of that electron spin with many of the nuclei in the quantum dot. So here I'm showing the red is supposed to represent the probability of the electron in the quantum dot. In here we have many nuclear spins. And there's about 10 to the 5 nuclear spins in a particular quantum dot. Now this may seem like a large number, but in fact it's the fact that there's a fairly low number, which means that this system forms a kind of coupled system where the nuclei depolarize the electron, but also the electron depolarizes the nuclei, and it forms an unstable coupled system. So let me explain that in more detail then. So I've just drawn a kind of diagrammatic of the interactions in this system. So the electron exerts a kind of effective magnetic field onto each of these nuclei. And the magnitude of this field is of the order of about 100 microtesla to about 1.5 millitesla. And that depends exactly on where the nucleus is in the quantum dot. So if it's in the center, the interaction will be stronger. Now the nuclei then exert a magnetic field back onto the electron. And again, this is a fairly small field. It's of the order of about 50 to 200 microtesla. So this is fairly small. And again, it depends on where the nucleus is in the quantum dot. So if you imagine that each of these nuclei have a spin, and now normally they'd be randomly orientated, and so the field onto the electron, the total field will be very small. But in fact, if we align all these nuclear spins, and we line them all in all the same direction, we find that the interaction energy can actually be very large. It's given by this hyperfine interaction constant here. And then we can actually calculate this as an exact value. So the interaction energy is about 260 microeV, which doesn't sound like very much. So our transition energy is about 1 electron volt. But if you actually calculate this in terms of an effective magnetic field, we find that this is about 8 Tesla. Now, for those of you that don't work in experimental physics, 8 Tesla is a very large field, and normally we need to use very large superconducting magnets to achieve this. And it's very difficult to achieve experimentally on a small scale. So this is actually a very interesting effect. However, I haven't yet explained why the nuclei cause depolarization. And in fact, what happens is that first of all you have a randomly orientated nuclear spin system. But the spins are kind of frozen in time over the timescales of less than about a microsecond. So you've got a finite number of nuclear spins here, and that means that the probability that they'll all be orientated to equal exactly 0 is very small. And in fact, you'll get a randomly orientated field in a particular direction, and the magnitude is about 20 millitesla on average. And this means that this electron here, which I've drawn as S, precesses around this magnetic field like this. Now, it does look like it loses spin information very quickly here, but in fact this is still coherent, so we still have information in the system. The real problem comes when the nuclei begin to change their orientation, and they do that over a microsecond timescale. So this arrow here will begin to change direction, and that really destroys the electron spin precession. Really, you can't predict then what will happen to it. Well, in fact, the direction of the nuclear spins changing is actually dominantly affected by the electron spin. So that each of these nuclei precess around the night field, the field felt from the electron. And they're all precessing at different rates. So slowly they will begin to change direction because this electron spin is depolarizing them. So in fact, you've got a coupled system where both of the systems are depolarizing each other. And this is why the spin is lost within about a microsecond. However, some more experiments that I did in Dortmund showed that the nuclear spin doesn't necessarily have to be detrimental. So here what we found, and actually it's fairly well known, that if you pump your system with polarized light, you'll polarize the electron spins, and then you transfer that polarization to one of the nuclei. You undergo a kind of spin flip-flop process. And if you keep on doing that, you go from a randomly orientated system to a system where many of the nuclei are ordered in the same direction as the electron. So here we have the situation where we have a small, randomly orientated nuclear field, and that system is unstable. But if we align the nuclear spins all in the same direction, we have a larger field pointing in the same direction as the electron. And so the electron doesn't precess about the nuclei, and the nuclei don't precess about the electron, and you formed a much more stable system. And in fact, we measured the lifetime of this system and found it to be about 0.3 seconds, so extremely long. Now, I should point out here that this is the population lifetime. It's not the coherence time, which is the oscillation that we measured before. In fact, if we wanted to really see if this was really useful for quantum computing, we'd have to measure the coherence time. But practically, in experiments, this is just very difficult, so that's why we haven't done it. But this already gives us an indication that we could be reaching very long spin lifetimes by aligning the nuclear system. So I've become very interested in nuclei and quantum dots, and so I have a few suggestions of how these can be used further. And one idea is to use these as kind of nuclear nanomagnets. So the idea here is that you align the nuclei and generate this is called an Overhauser field here. It's just the nuclear field. And it can be in a controllable field strength up to 8 Tesla. And also, you should be able to generate this in any direction you like. And in fact, because the nuclei themselves only field very, very small fields, either from the nearest neighbours or from the electron, it's very easy to change the direction of these fields using just millitesla fields. So you can imagine a system where you have many quantum dots, each of them you excite singly with light to control the magnitude of the field, and then you control a small magnetic field to change direction. So each of these quantum dots can have its own magnetic field, and that's very different. That's impossible to achieve in a superconducting magnet, for example. So we might use this nuclear spin to stabilize the electron spin, or even to manipulate it. For example, if you have one here, then the electron spin can precess in a controllable way. Another suggestion I've calculated and I plan to work on in Bristol is using the electron spins to read out a single nuclear spin flip. So I showed you before that in the ensembles we measured precession of the electron spin in the magnetic field. And I want to do now is measure this precession period in the nuclear Overhauser field. Now it turns out that if you do this, if you measure the frequency, you can measure field changes down to very, very low fields. And I predict that we should be able to reach an accuracy of about 200 microtesla. Now this magnitude of field is approximately the order that arises from just a single nucleus. So if we are able to flip a single nucleus from one direction to the other, we should be able to measure that using this technique. I'll explain how we actually measure the precession in a minute. So this could be very useful because nuclear spins in these systems generally are extremely stable. So lifetimes of the nuclear spin systems have been shown to be hours or even days. So really you could start thinking about using single nuclear spins with this electronic readout here to process information in nuclear spins and read it out with an electron, or even later using light. The second advantage of this is that you don't need isotopically pure material. So as long as you keep all of these other spins in exactly the same configuration, and they should do because they have very long spin lifetimes, you can manipulate this spin and still read it out. And that's got huge advantages over other proposals that I've seen. Okay, so I seem to be running, no, it's okay. So I want to talk about the second part of my talk, which is looking at controlling the interaction between light and the transition in the quantum dot. And now I'm going to talk about work that I did in Sheffield. And we actually do that by incorporating quantum dots lithographically into microcavity structures. So I'm showing you two examples here. We have a micropillar device And this was fabricated in Sheffield. And here we have a system where we have, these are called distributed Bragg reflectors, and they essentially act as mirrors. So they reflect the light downwards and upwards here. And in fact, we've created a small cavity here, which I've coloured in red here. This cavity actually contains the light, and the idea here is that the light contained within these structures over a very small volume, so this is a 1 micron across here and about 10 microns height here. Any emitter that you put inside here will have a greatly increased interaction strength because the light is confined over a small volume and the light's actually trapped in there for longer than if the quantum dot was emitting it. And the same idea is contained within these photonic crystal devices. And the idea is that we put a layer of quantum dots throughout this structure. So the quantum dots are about 3 orders of magnitude smaller than this image here. And look at the interaction between the emission of the quantum dots into the cavities here. So I'm going to explain these photonic crystal cavities in more detail now. So a photonic crystal then is basically, here we have a 2-dimensional lattice seen from the top. And you have an array of holes which gives you a modulation in refractive index. And this modulation in refractive index essentially acts in exactly the same way as what you see in a semiconductor for electrons. It creates a photonic band gap. And that essentially means that any light in the structure can't propagate over this photonic band gap. So to fabricate this practically, what we do is we make this photonic structure using electron beam lithography, and then we etch through the holes and then etch underneath the structure as well. And the idea here is that you have a confinement in the lateral direction, but also in the vertical direction due to total internal reflection. What you then do, or in fact when you design the cavity, actually you take out one of the holes, and you can see here there's a hole, there's a place where the hole should be. And the idea here is that will create a kind of cavity in your photonic crystal, and it's very small. It's of the order of about less than 1 cubic line width, wavelength here. So we do that, and then we also into these devices, we actually incorporate a layer of quantum dots, and we hope that one of these quantum dots has the right energy which matches the modes of these cavities here. We also use micropillars. I'm showing you a good example of this, and we use micropillars mainly as single photon emitters. Now, we use these because, in fact, by taking off a few of these mirrors at the top here, you'll find that all the light is channeled into the vertical direction. So we have the increased interaction, so it emits photons faster, and you can actually channel the light upwards, and it's much easier just to collect the light then. So in a normal semiconductor with the quantum dots inside, most of the light is totally internally reflected, and it's very difficult to collect it. So here I'm showing you some PL spectra from some quantum dots inside the pillar. So they appear at random places, but they're emitting into the cavity, and we see that we have fairly high count rates of about 20,000 per second using an 80 megahertz pump laser. What we do with that signal then is try to show that it's actually producing one single photon every time we put in a pulse. So what we do is we take the emission and we divide it into 2 and detect with 2 photon detectors. And this is called a Hanbury-Brown twist experiment. And the idea here is that if it's a single photon emitter, the probability to measure 2 at exactly the same time should be 0. And this is what this curve here shows. So here, what we do is, we're showing a long time, t equals 0 here. Now, if you look 12 nanoseconds later, we measure a first photon, that's our start signal, and then when we see the next photon, and we see it 12 nanoseconds later. And that's because 12 nanoseconds later, we have our second pulse. So this is why we see a series of peaks here. But if you look at exactly time t equals 0 here, we see that the probability that we have 2 photons arriving at the same time is 0, or in fact it's about 7% because these devices aren't perfect. So you see that these quantum dots make very good single photon emitters. And if you have very good single photon emitters, there's many of these quantum computing proposals that we can actually implement. Okay, so I just want to summarize the progress in quantum dot cavity QED so far. So a lot of the research into quantum dot cavity QED has been on achieving the so-called strong coupling regime. So this means that the quantum dot emits a photon, and the photon is emitted into the cavity. And in fact, the photon remains in the cavity, and the interaction between the quantum dot is so strong that the quantum dot actually reabsorbs that photon again. And by looking at the spectroscopic characteristics, we should see a dress state then. And so a lot of people have been working on achieving this strong coupling regime, because if you can do that, that means we're on the first step towards having a deterministic coupling of the quantum dot and the light. So that means that you shine in the photon and you know what's happened to it. So in fact, this was achieved almost simultaneously for micropillars and for photonic crystals, and reported in Nature here. And this was done in 2004, so about 4 years ago. And more recently, improvements have been made to this scheme, so strong coupling has been shown to be more predictable, and in fact it's also been achieved for electrically gated systems, which practically is much more is very important for us, because it means we have a lot more control over the system. Also, efficient single photon sources have been achieved of about 25% efficiency, so we're getting to the point where we can press a button and produce a single photon on demand. Okay, so I said earlier now that, so we've achieved this strong coupling regime, but we want to read out single electron spins. So I want to talk about how we can do that then. Well, if you remember before, we used this Faraday Rotation technique, where we shined a linearly polarized light onto the sample and looked at the rotation. We did this on ensembles before because it was very difficult to see the signal in normal quantum dots. But if you put your quantum dot into a microcavity like a pillar, you actually increase the interaction strength by many orders of magnitude. And therefore it should be possible to see a rotation of the light due to just a single electron spin. And in fact, this was achieved by Berezovsky and co-workers in this paper here in 2006. And you can see here's the energy where the quantum dot is. It's quite difficult to explain exactly what's being plotted here. But here you measure the rotation in microradians here of the probe pulse as it passes through this quantum dot transition, and they've reached about 200 microradians. Now I've got to point out here this is quite a low rotation, but in fact they measured a very low quality cavity. They didn't have any lateral patterning, and the Q factor was about 50, and the kind of structures we're looking at have Q factors of about 5,000. And it's actually been predicted that if you're close to the strong coupling regime, the rotation of the light going in and out of here should be through about 180 degrees. So you should see very, very strong effects. So what can you do then if you can achieve the measurement of a single spin using this technique? Well, there are many different proposals, particularly for quantum computing and for quantum repeaters and so on. But I just wanted to highlight a couple of proposals by my colleague at the University of Bristol. Now, here, what he's proposed is using a remote entanglement of two spins. So the idea is you have two spins in a cavity, one cavity here and one in the other cavity, and you input a photon into this cavity that's in a superposition state, and this will put this quantum dot also into superposition state. Then you go on to the next cavity and entangle this electron with the photon as well. And this implies that these two electrons are then entangled. And then you detect that photon to measure these two states to check the entanglement. So that in that way, you'll be able to entangle two spins remotely. And that's very important because that means that you can send in a photon to many different cavities, and really you've got a scalable system. You're not limited to how many quantum dots you excite. The second proposal is to entangle not the electron spins, but the photons. And the idea here is, again, you have a cavity, and you put your spin into a superposition state. So you pass a superposition state of polarized photon into the cavity, it becomes entangled with the spin, and then the second photon comes in and becomes entangled with the spin. And so that means that the two photons are entangled. And you can do these for many photons, and you end up with GHZ states, so highly entangled photon number states. However, when you look at these schemes, you realize one very important thing, and that's that the cavity that you're using must preserve the selection rules in the quantum dots. All of these schemes require that the interaction between the photon polarization and the electron spin is preserved. And that means that the cavity must not affect the polarization. And that's actually going to be a big problem. So I'm going to talk about photonic crystals now and some work that we did at Sheffield to look at the polarization. Now here I'm showing you a detailed picture of one of the cavity structures that we use. And this is a cavity where we take out 3 of the holes in the line here. Now we use this particular structure because this is the only cavity structure which so far strong coupling has been observed in. So it's actually a very important structure for us. Now through this structure there are a layer of quantum dots in the center, so there's many quantum dots in the center of this cavity here. And here we can see the emission of many of these quantum dots. So they emit over a wide range of wavelengths here. So this is without this cavity here. But if we then fabricate the cavity, what we see is that the emission is now redistributed into several modes of the cavity. So here you have the fundamental mode, which is very sharp. So this is a resonance with the cavity system. And you see higher order modes which don't have such high quality factor. Now what you notice here, what we notice is that all of these modes are very strongly linearly polarized. So the first 2 modes are very strongly vertically polarized. So blue is in vertical polarization, and these 2 are strongly horizontally polarized. So the red is horizontal polarization. So you see really they're between about 70 and 100% polarized. So what happens to the quantum dots then if you put these in the cavity? Well, what we did with this structure was simply lower the excitation power that we're looking at, and that means that we can make out the sharp individual lines coming from each quantum dot. So what we did then, and you can see here this is some indication of these kind of sharp features here, but you lower the power and you see them much more clearly. What we did then is measure the polarization of each of these quantum dots as a function of where they were spectrally for this, where these modes are here. And what we found is that the quantum dots emitting around this mode are very strongly horizontally polarized, and the quantum dots emitting here are very strongly vertically polarized, and there's a crossover in between. So there's a very clear indication that the quantum dot polarization is strongly affected by the cavity, and in fact the cavity almost acts to filter the polarization. So obviously this is not good news if you want to measure the electron spin in the system. The second problem with using photonic crystal cavities, and that's that many of the proposals we want to do involve exciting them along a waveguide. Now, until now, almost all of the work on single quantum dots has been done in a particular geometry. So if you have the quantum dot here, in this kind of cylindrical shape here, you excite the laser from the top and then collect the light in the same direction along the Z direction. And you can see that this has a kind of cylindrical symmetry. However, in the waveguide geometry, you want to excite it from the side along here, along this X direction here. And in fact, it could be that the selection rules in these quantum dots don't get preserved anymore. If you look at this quantum dot, you can see that the oscillator strength along this direction might be different than along this direction. And in fact, it's only very recently that the excitation of quantum dots in plane for single quantum dots has actually been observed. So here, in Muller and co-workers, they actually excited the quantum dots resonantly and collected the emission this way. And they didn't yet look at the polarization selection rules. So I think there's a lot of work that has to be done, really, on investigating the selection rules before we can use quantum dots in this geometry. So the question is, for these kind of schemes, should we use micropillars or photonic crystals? And first you might think we should use micropillars. And the reason for that is that the micropillars can be easily fabricated to be very, very circular. So we can achieve about 10 to the minus 4 ellipticity here. Also, the emission is highly vertical, which means it will emit very strongly in the vertical direction, and so it's just easier to collect the light. However, we want to make scalable quantum computing systems. And if you want to do that, you need to be able to direct the photon out of this pillar and into another pillar somewhere else. You might be able to do that with 2 pillars. You might even think of some scheme where you can do it with maybe 10. but certainly trying to do any more than that becomes very, very difficult. It's not easy to see how you would do that. On the other hand, photonic crystal cavities are also very successful, and in particular, they're very easy to integrate into photonic circuits. So here I'm showing you a paper by Faraday and co-workers, and here we have a waveguide going on here, and the cavity is just a few holes away, which means the cavity interacts with this waveguide here. So you send in a photon, it interacts somehow with the cavity and gets sent along to the next cavity along. So really it's very easy to make these circuits. But we do have the problem, of course, that these photonic crystal cavities, but also these waveguides are strongly polarizing. So we need to overcome that. Now I should point out here that even though these cavities are strongly polarizing, in fact, in the literature there's been almost no work done on trying to control the polarization of these cavities. There's really very little work done into it because nobody's really considered these facts yet. So I think with a bit of effort in this field, we should be able to achieve non-polarizing cavities. So I just want to finish now by talking about what I think the future is for quantum dot spins in photonics. And I think, as I said before, the future will be in photonic circuits. Now I'm showing you a diagram here published by Simon Devitt and co-workers in Physical Review A recently. And this is for a so-called photonic module for generating spin polarization entangled so-called GHZ states. Now I'm not going to go into exactly how this works, but I just wanted to show you the components here. So these red dots represent quantum dots, and you can see we have a photonic crystal cavity here. So in this system then, we have a single photon emitter, that's a quantum dot here, inside the cavity, and the control of whether we read it out or not is done by another quantum dot in a Q switch. So we turn that one on and it gets sent through the waveguide, it then gets coupled into a second cavity here, and in here we have the interaction where we generate our spin-polarized photons here, the polarization entangled photons. So, and then we let it out of the cavity and it travels along a waveguide to the next part of the photonic module. And the idea here is that you create many of these things and join them all up together. Now, I just wanted to show you this because I want to point out the things that we experimentally need to achieve before we can actually make one of these structures. So I should point out that this interaction is using a spin-dependent interaction. So we need to, first of all, as I've said before, preserve the polarization somehow in these structures. But we also need to achieve deterministic interactions because we want to know that if we send in a single photon into this system, we need to know it's interacted in the cavity in the way that we want. We can't really rely on probabilistic interactions because we're looking at making these structures very large. We also need good single photon sources, and we're well on the way to that. And now the final thing, which I want to talk about next, is making sure that each of these quantum dots here has the right wavelength that matches the cavity. So all these dots have got to be the same, all the cavities have to be the same, and we also need to place the quantum dots exactly in the center to increase the interaction as much as possible. And I want to talk about how we can do that next. So quantum dots then, the ones that we look at, these are self-assembled quantum dots. And self-assembly is a crystal growth technique which produces very high-quality quantum dots. So what you do here, I'm showing you an AFM image of these quantum dots. What we do is deposit indium arsenide slowly onto gallium arsenide. And that allows the formation of these so-called nano islands here. Now these islands form spontaneously, and they're in a random placing on the crystal structure, and they also have a random size. And that size determines the emission energy of the quantum dot. So even though these make have very good optical emission properties, this is not what we want. We want to be able to control exactly where our quantum dots are and what wavelength they have. So some work has been done by Schneider and co-workers in this paper here, where they try to control exactly where these quantum dots appear by creating a strain field underneath the quantum dots when they're grown. And that works fairly well. You can probably just about make out there's an indentation here, and these are markers to show whether the quantum dot is where it should be. And really they've managed to put the quantum dots within about 10 nanometers of where they want them. So really this is what we need to achieve. There is a problem, however, because it turns out that the photoluminescence characteristics of these quantum dots just isn't as good as these quantum dots here. Now nobody knows why this is yet, but I'm sure that we'll be able to overcome this problem in the future. So you have the quantum dots in the place where you want them, but these quantum dots also have different sizes, which means they have different energies. And you really want to have the energy to be at exactly the same wavelength as the mode of your cavity. So you need to be able to change the wavelength of these quantum dots. And some work was done recently by Rastelli and co-workers in this APL that I've shown here. And here they use laser annealing. So what they do is they take a microscope objective and focus on one of these quantum dots here, and they measure its emission energy. And then they take a high-powered green laser and shine it onto the surface. And it's such high power, you send in a pulse of light and it almost melts the quantum dot. It kind of ablates it. And that changes its composition profile. And if you do that, that shifts the energy. So if they do this very carefully, they could send in a pulse of light, measure again the emission energy of that quantum dot, see if it's the right energy. If not, then blast it again. And if they keep on doing that, they can predict exactly, in this diagram here, this is the change in energy, they can predict exactly where the quantum dot will emit. So really this is some very nice work. So if you combine these techniques, you've then got a system where you can place the quantum dots where you want with the right energy. And I think in the next few years this will really be achievable. So I'm going to reach some conclusions then, so we have time for questions. So my aim in this talk was to see how far are we along to making photonic circuits, where we have a spin as a static qubit and a photon as a flying qubit, and we're using quantum dots for that. So the progress so far in this field is, first of all, that we've achieved long spin electron coherence times, and these should be improved further if we investigate this system. We have good single photon sources, and again, I think with improvements, they'll become extremely high quality. And we've also achieved the strong coupling of the quantum dot transitions to the photonic modes in our photonic structures. So we're on the way to achieving deterministic interactions. However, there are some challenges for the future, because we've got to get this strong coupling regime, but also the spin-dependent interactions achieved simultaneously, and that's going to involve redesigning our cavities. We've secondly got to achieve a complete control of where the quantum dot position is and its wavelength. And again, I think this should be achievable within the next few years. So actually, I predict that within the next 5 years, we may just about be in a position to make one of these photonic modules. Okay, so to finish then, I'd just like to acknowledge all the people that I've worked with that have helped me produce some of the data that I'm showing you. So I've been measuring photonic structures at the University of Sheffield, and here I've listed the students I've been working with, PhD students, in both experiment and in theory. Here are my supervisors here, and these two guys are quantum dot growers. They make the very high quality quantum dots that we see. And these structures are then fabricated at the University of St Andrews into photonic structures. And this is a very difficult technique, so really these people deserve some recognition. And I'd also like to thank Gopal Venu Ashanta, who's been, for the past week, looking after us at the TIFR in Mumbai. We actually have a new collaboration with him where we're going to take some of these techniques further. And this is actually funded by the UK-India Education and Research Initiative. And then just finally, I'd like to thank my former co-workers at the University of Dortmund, where I had my Alexander von Humboldt Fellowship. So thank you very much for your attention.